I'm Blake Anderson. I'm the Executive Director of Academia Research Solutions. We're a Section 501c3 nonprofit organization, and our mission is to promote responsible development and persistent support of software technologies and research. We provide software and administrative services to help researchers create the next generation of research technologies and keep the last one running. Back in the day, researchers would get funding and they would buy servers, so they'd have to pay for rent, for power, and internet connection. Then, with the invention of virtual machines, researchers were able to share their resources between projects and between collaborators. The cloud provides a new level of sharing with virtually unlimited resources. Even with cloud resources, there are a lot of considerations and challenges. What happens when funding ends and there's no budget to continue operations? Who's going to maintain the software when technologies change, students graduate, or vendors move on? Can the project stay online after a user complaint or security breach triggers a compliance audit? Under a traditional approach, the answer would be to charge it to the customers. But this is obviously not an option in research. When you're Facebook, you can just recruit more users and sell more ads to generate more revenue, but research doesn't work this way. Usually products are available for free, or they're made available to underprivileged populations, and researchers have no interest in generating revenue to support their infrastructure. So Academia Research Solutions set out to design a system. It had to be simple, it had to be easy to upkeep, it needed to be resilient to funding gaps, and it needed to enforce the security and compliance best practices that students often leave out of their design. One of our core technologies is Docker, specifically Docker Swarm. Docker containers, if you're not familiar with them, function as independent servers that allow each application to operate in its own unique environment. Because the containers are based on images that can be built from Linux, it's possible to create a diverse ecosystem of technologies, and containers are scalable by design. It's easy to spawn multiple instances of a container if traffic gets heavy or you need more database computation. This slide is a little too complicated to go over during the presentation, but I wanted to demonstrate our network architecture. We start by funneling all of our traffic through a Trafic instance on a load balancer, which then pushes traffic to a number of Swarm worker nodes that are able to respond to any requests that come through. There are other benefits to using our design, including sandbox development environments and versioned code releases. It also facilitates multi-institutional collaborations, and it's safe for highly sensitive data such as patient health information. We do a few simple optimizations to get people started. For one thing, we can look at optimizing containers by moving to Alpine Linux. For example, the default Ubuntu image starts at about 400 megabytes, but Alpine runs at about 5 megabytes. This can significantly reduce the need of your container size. We also take a look at the RAM usage. For example, WordPress can eat up to 180 megabytes of RAM just to run a basic content management system. Our containers usually run at about 2 megabytes of RAM, so that's a significant improvement. We take advantage of Docker's layered design to share common system elements between containers. A poorly built container can be a couple gigabytes in size, but if you build them well, you could add 100 kilobytes to your stack with a deployment. So I wanted to go over a specific example of how our system can help a typical research project. The source code that I'm showing you is based on simple examples from W3 Schools. You can see someone is putting in their database credentials, connecting to a database, and then printing some results to the screen. And this might look like any research project that you've ever seen before. Unfortunately, there's a lot of bad practices that are going into this example. At the top, you can see the credentials being stored in the script file may cause them to be stored in a code repository and exposed to anyone else who has access to the repository, especially if it's an open source project. The system also has SQL injection vulnerabilities where someone who was trying to attack the server could inject their own query details into the example to read or destroy data at will. and the site is vulnerable to cross-site scripting. By printing unsanitary user data, it's possible for an attacker to execute arbitrary JavaScript and attack the users of the system, possibly gaining access to their account and doing damage to research data. So instead, we promote what we call API-centered design, which is basically separating the front and back-end logic. We consolidate the database logic to controlled endpoints, usually in a REST-based interface. This also allows multiple applications to share these endpoints, or even your collaborators can build applications and use controlled access to get to your data and perform analysis. This approach also isolates the sensitive portions of the code and allows your daily development to work with code that doesn't have to worry about security vulnerabilities. So if we were to take the example that I just showed you and convert it to our architecture, we would start by moving the database credentials into Docker secrets. These are configurations that are loaded at the time that the production environment is booted up. And this approach also allows your developers to create their own development credentials, and while they're developing on their local machine, they can access a separate database, so they're not interrupting production workflows. We would limit the database access so that users only had access to their own project. This is really important because SQL injection attacks are extremely common, and it's unlikely that developers will be able to eliminate all of them. So we want to make sure that if damage can be done, it doesn't affect other projects on the system, and it's limited only to your own users. We provide these isolated containers for each application so that you won't be affected by other projects' mistakes. For example, if another user of the system has a file upload vulnerability, they'd be able to manipulate the files of your system, and having containers keeps that from happening. So you can read our paper for more details on our methods. We share examples of doing simple performance tweaks to reduce the overhead on scripts, choosing frameworks that are resource friendly and use fewer resources for hosting, and designing special considerations for large scale and data intensive systems. In the end, we're able to create a simplified development and deployment process that creates a safe and secure environment for shared resources, and our preliminary systems are able to deploy dozens of applications, and we think that it's possible to host hundreds or thousands on a very small Docker swarm using our approach. So we were able to show that using the techniques and methods of our system, we're able to create an affordable cyber infrastructure for software-based research, and that it's actually feasible to keep these projects running beyond their funding award period. And that's important so that the projects can continue to collect data for analysis, to apply for future iterations of funding, and for any commercial growth potential, as well as benefiting the public. This work was supported by the University of Missouri, and thanks for listening.